Thank you all for coming this evening. My name is Len Shustak. I'm the chairman of the board of the Computer History Museum. There are seats, by the way, so people who are standing don't need to stand. You can take the seats in the back there. This is going to be a terrific evening. I hope you saw the machine on your way up, and if you were here early enough, you saw it being cranked. This is really an auspicious occasion. We're here celebrating the arrival for the first time on this continent of Babbage's Difference Engine. It's a 9,000-pound mechanical calculator designed in the 1840s that automatically and with 100% accuracy prints and calculates mathematical functions. It's a sumptuously beautiful machine. Even standing still, it's like a piece of sculpture. And when it's in motion, it's magical and hypnotic. We are, by the way, delighted that it works. When it came here, it wasn't obvious that it would, because it was quite shaken up on its arrival, and we had two engineers here from the London Science Museum where it was built working to make the machine work. And now it works most of the time. We're hoping it'll get to the state where it works all of the time. But it is an amazing machine. We're actually here celebrating two different dreams. One of them was Babbage's dream, and that was to design a machine that would compute by steam instead of by pencil and paper, so that math tables would have no errors. He analyzed math tables of the day and found lots of mistakes and wanted a way of producing them without any mistakes. His design was never built. Babbage died a bitter, disappointed old man. It was a grand dream, but it was one that was never realized. The second dream was Doron Swade's. His dream was to prove that Babbage, in fact, was not a failure, but that he was a genius. Doron's dream of building Babbage's design for the difference engine started about 20 years ago. Unlike Babbage's dream, Doron's dream was realized. In fact, it was realized twice. There were two of these engines. The first one was finished in 2002 and is in London at the Science Museum. And one was finished last month, and that's the machine that's on display downstairs. This is not a production line. I can assure you that this is most likely the last Babbage full-size difference engine that will ever be built. This is an heroic project, and it's a project that definitely fits squarely into the mission of the Computer History Museum, which is to understand and to explain the origins and the development of computing. We've been doing that now for more than 30 years. And we have, by far, the largest collection in the world of artifacts and objects describing the information revolution. We have about 40,000 physical objects. We have something like 30 million pages of documents. We have thousands of photos and videos. We have hundreds of oral histories of pioneers of the computer revolution. We have several physical exhibits downstairs and a really big physical exhibit that's currently in construction that should open in the fall of 2009. And our website, we have about 10 cyber exhibits, including one in development to match the physical exhibit that's going downstairs, plus access to our catalog and to some of the collection. At this point, I think it's fair to say that we're the premier institution in the world that's preserving and communicating the objects and the stories of the information revolution. Note that word revolution, right? All revolutions have revolutionaries and have founding fathers. And in that sense, Charles Babbage is one of the founding fathers of the computing field. So it's entirely fitting that we celebrate the man and his creation tonight. Inspired projects like building the Babbage Difference Engine require inspired supporters, and I'd like to thank a few of the people who caused this to happen. That list starts with Nathan Myhrvold, whom you'll hear more from this afternoon, for commissioning the second engine after seeing the one in London, and for loaning it to us so that it can appear downstairs. The second is the London Science Museum, and Doron Swade and his team there that built both engines and their attached printers. The third are the CHM donors. We had to raise something over $100,000 to finance the transportation and exhibit that surrounds the Babbage engine. And I had about 2 weeks to do it, about a year ago, January. I sent an email to Andy Bechtelsheim, and 7 minutes later, he said, okay, I'm in, I'll be the lead donor. If only the foundations we've been talking to were that fast in making their decisions, fundraising would be a whole lot easier. But with that lead donation in hand, we were able to get 6 other people to contribute to the project. And they are Gordon Bell, representing the Bell Family Trust, Judy Estrin, Kathy Calder, representing Fry's Electronics, Grant and Dorrit Seviers, John and Marva Warnock, and Donna Dubinsky, my wife, and I. The engine is here because of that list of people. Please let's give them a round of applause. I don't want to talk very long because we have much more interesting things to listen to than me. The structure of the rest of the evening is as follows. I will introduce Doron Swade, who will speak about Babbage and the engine. Doron will then introduce Nathan Myhrvold, who will talk about his interest in Babbage and how that came to be. And then we'll retire to the easy chairs and answer questions. If you'd like to ask a question, there are cards on your seat. Fill out the cards, and a little bit later, pass them down to the aisle. They'll be collected, and we can use them as input to the question process. I'm delighted to formally introduce Dr. Doron Swade, whom it has been my pleasure to know for almost a decade. Doron, like Babbage, is a polymath. He's an engineer, an historian, a researcher, a museum curator, an author, a lecturer, a professor, and the world's preeminent Babbage scholar. To show you the variety of this man, look at his background. He has a bachelor's in physics and electronics, a master's in control engineering, and a PhD in the history of computing. He was the senior curator of computing at the Science Museum in London for 14 years, and then assistant director and head of collections. He's written 3 books and over 70 scholarly papers and magazine articles. Doron is also a wizard. He's the wizard who has brought to life for us the creation of a 19th century genius for all of us to enjoy and to learn from. Please welcome Doron Swade.
Len, thank you very much. You're running. Thank you very much for those very generous remarks. I have a story to tell you about Len. There was some question whether we could actually build the second engine in London after the first engine had been completed, and I wrote to Len in 2002 and to explore the prospect of possibly building that engine here, and responded almost immediately and said, I would do handsprings to have that engine here. I have fulfilled my side of the bargain. And if without risk of injury we can encourage Len to fulfill his side, perhaps that's how we can end the evening. I've been asked to say something about Babbage, and Len has limited me to 4 hours. I find that entirely churlish, because Len knows absolutely that the short version takes 4 weeks. So I've arranged sleeping accommodation in the Grand Hall, and the best thing is probably to kick off. Okay, what can I tell you in 15 minutes about Charles Babbage? One is I thought I'd give you some sense of his times and what kind of man he was. I thought I'd say something about what he accomplished and why he tried to accomplish it. And finally, something about Difference Engine No.2, that rather sumptuous piece of engineering sculpture down in the lobby. So, what sort of world was Babbage's? Well, we pride ourselves now in living in an age of innovation. Barely a day goes by where there isn't some breakthrough, some new discovery, new innovation, some silver bullet, some new technological solution to something or other. The thing is that the Victorians shared this frenzied sense of change. The middle decades of the 19th century were a time of unprecedented engineering ambition. Products poured from the new manufactories. There seemed no limit to new processes, new products, new materials. England was in the throes of the Industrial Revolution. This was a time of contraptions, of contrivances, of devices, of invention and innovation. This was Babbage's world. Thomas Carlyle wrote, it was the age of the machine, it was the age of machinery in every outward and inner sense of that word. outward and inner sense. It wasn't just the conquest of nature and the external world by technology. This was an inner sense. Mechanics became the terms in which people understood the world. To understand anything at all became coextensive with mechanical explanation. It seemed that there was no predicate in nature or human experience that could not be exhausted by mechanical explanation. So this was Babbage's world. These were the terms in which he saw the world. The title of the book on Babbage, the English version anyway, is called Cogwheel Brain. The idea was to capture somehow this ambiguity between internal and external, the terms in which one saw things, the currency of thought, as well as the imposition, if you like, of man's will through technology on external life. Now, the devices of the Industrial Revolution have one thing in common. They all involve physical labor. So machines of that era were all designed to relieve or replace physical labor. But there was another revolution in the making, and one that has received less attention, largely because it failed. And that was the mechanization of mental labor. More specifically, the mechanization of calculation through calculating machines. The idea is that you could have a machine that could produce something which up to that point in time could only be achieved by thinking. So this was Babbage's extension of the model of industrial production from things to thought, from physical labor to mental labor. And Babbage, of course, was the pioneer. He was at the vanguard of that movement. And that's one way of placing him in some historical context in the Industrial Revolution. This was the extension of the model of industrial production to thought, to thinking. And we'll see how his difference engines were actually the birth of the idea of intelligent machines. So who was Babbage and what did he do? So I'm going to run through three quick portraits to give you some thumbnail sketch of who Babbage was. This is Babbage in 1813 and his fiancée Georgiana Whitmore, who he married in 1814, the same year he graduated from mathematics at Cambridge. He married Georgiana against his father's wishes. His father was a wealthy banker, thought it imprudent for somebody to marry without independent means, and Babbage ran away, in a sense, and married Georgiana. It was a very, very happy marriage, but tragedy struck in 1827, where four close members of Babbage's family, his father, his wife, Georgiana, to whom he was absolutely devoted, and two of his children died in the same year. Babbage was inconsolable. He never really recovered in some sense. He never remarried. So 1827 was a year of black tragedy for Babbage. This is Babbage, esteemed man of science. That's an oil painting in the National Portrait Gallery by Lawrence. And Babbage, age 53. This is Babbage as somehow rehabilitated. In 1830, Babbage published a savage attack against the Royal Society. He impugned the personal probity of its senior officers. He attacked them for their incompetent governance of science. The incontinent savagery as of his attacks and the sarcasm effectively wrecked his political life in science, wrecked his scientific political life. By this stage, he was already partially rehabilitated. He published Economy of Machinery and Manufactures, which is a turning point in economic history. So this is him as an esteemed man, memorialized, if you like, in this oil painting. This is Babbage. This is what I call his Beethoven look. This is Babbage, 1860, the last known portrait at the Fourth Statistical Conference in London. And this is Babbage, a venerable grump. Disappointed, professionally unfulfilled, self-perceived failure. So without doing violence to the richness and complexity of any man's life, we can see a trajectory here. You have the radicalized student. The portrait, the resemblance to Napoleon is not accidental. Babbage supported Napoleon. England was still at war with France. This was 1814. Napoleonic War was finished 1815. You have a radical student supporting the enemy. You have a man who is capable of political suicide by defending propositions that would actually lead to his academic destruction. He graduated without honors, it is thought, because he tried to defend a proposition thought to be blasphemous. You have a bold, vigorous, independent, radical student. You then have the transition to the man of science. And this is Babbage around the time, it's a daguerreotype by Claudet, around the time he did Difference Engine No.2. So this is Babbage, still with some youthful vigor, beaten up by government, still slugging it out, still trying to design his engines. He'd given up building them by that stage, but that is perhaps a very telling portrait. So, Babbage, raconteur, socialite, sought after dinner guest. He's brilliant, boldly original, a man of fierce loyalties. His friends could do no wrong, his enemies could do no right. He ached for honours and complained that the Lucasian chair was the only honour bestowed on him by his country. You have a complex figure. Babbage, we know, failed to build any of his engines, and the reasons are a rich cocktail of historical, political, financial, and technical factors. One factor was the entrepreneurial climate, something perhaps dear to people's hearts in Silicon Valley. So let me give you a flavour of Babbage's writing. This is Babbage in a very obscure paper on taxation, writing in 1851 about the entrepreneurial climate in England. Propose to any Englishman any principle or any instrument, however admirable, and you will observe that the whole effort of the English mind is directed to finding a difficulty, a defect, or an impossibility in it. If you speak to him of a machine for peeling a potato, he will pronounce it impossible. If you peel a potato with it before his eyes, he will declare it useless, because it will not slice a pineapple. Impart the same principle or show the same machine to an American or to one of our colonists, and you will observe the whole effort of his mind is to find some new application of the principle or some new use for the instrument. Anyone who has seen that engine run downstairs and sees that scything motion of those razor-sharp things will be convinced it would slice a pineapple. So in Babbage's dim view of the entrepreneurial climate in England, we have the familiar refrain, and that is that European innovation versus US commercial exploitation of markets. The engines. The Genesis episode was in 1821, when Babbage was sitting with his friend, the astronomer John Herschel, 1821 in London, checking manually calculated tables. He became increasingly dismayed at the errors. These were tables calculated by computers. Computers in those days were humans, not machines. And he became increasingly dismayed by the number of errors. And he clasped his hand to his head and he said, I wish to God these calculations had been executed by steam. Steam was a metaphor for two things. Firstly, the infallibility of machinery. Machinery, the unerring certainty of mechanical agency, would eliminate human error from the production of tables. But steam was also a metaphor for production. The machines would solve the problem of supply. There were astronomers who were seeing asteroids and they thought they were new stars. And they wanted tables to plot their trajectories. And they pressured the Greenwich Observatory to produce the tables who didn't. Why was Babbage sitting there doing astronomical tables with Herschel? Because the political pressure from the amateur astronomers was to leverage Greenwich Observatory to produce these tables at the cost of government. That's why he was sitting there. They had a problem of production, and engines would solve this. As Babbage's son put, the engine would be a manufactory of numbers. He was extending model of physical production to the production of things which, up till that point, could only be acquired by thought. So Babbage set about. He devoted the rest of his life to trying to build these engines, designing and building them. This is the plan of Difference Engine No.1, which he conceived in 1821 and designed and developed. This is 1830, so he designed and developed this for over 30 years. He built only 1/7 of it. And that is probably the most celebrated icon in the history of computing. That is 1/7 of the full-size Babbage Difference Engine No.1. It sits in the Science Museum in London. And this was the device that sat on Babbage's mantelpiece at his soirees. And I will explain to you, there's a lecture on May the 1st. This is a very short lecture, so you can relax. There's a longer lecture where I'll explain to you why Babbage thought God was a programmer. And I thought those of you in the software industry may be flattered to know that. And I'll explain more fully about that on Saturday the 10th. There is a lecture which is a fuller one than this. So this machine, I said it was probably the most celebrated icon on the prehistory computer. It is the first automatic calculator. It's first successful automatic calculator. Now that sounds rather banal to say, and it cannot be overemphasized how important that statement is. The machine is operated by cranking a handle, which is up there. You enter numbers and you crank a handle. The point about it is automatic. That is to say, the operator does not need to understand the mathematical principle on which it's based. It does not need to understand how the machine is worked in order to get useful results. By exerting physical energy, you can get results which up to that point in time were only achievable by mental effort. Now, this is the first successful transference of human intelligence to machine. reverse. This is the first successful ingression of machinery into psychology. You cannot have autonomous machines, you cannot have intelligent machines, you cannot have computational machines until you have autonomy. And the significance of this machine, one of its significances, there are at least three, is that it's the first successful automatic calculator, the first successful transference of mental process into it. And the significance of this as a thinking machine was not lost on Babbage or his contemporaries. Harry Wilmot Buxton, a junior colleague of Babbage, wrote, "The marvelous pulp and fibre of the brain had been replaced by brass and iron. He, Babbage, had taught wheelwork to think, or at least to do the office of thought." That's Buxton. Lady Byron, that's Ada Lovelace's mother, wrote in 1833 in her diary, "Last week we saw the thinking machine, for such it seems." So the significance of this machine was not lost on Babbage's contemporaries. Okay, I'm quite sure there are probably some tech wonks here. Thank you. I will just run through some of the logic of the circuit and systems functions that are present in Babbage's difference engine. I'll rattle through these. They may mean things to some and not to others. Parallel bus, microprogramming, pipelining, pulse shaping, binary latching, polling, input-output, bounce catcher, Schmidt triggers, and serial USB. The last one was a test to see if you were awake. Babbage failed to build a complete machine, and he returns time and time again in his writings, sometimes in dismay, sometimes in despair, sometimes in anger, but in disbelief at the dismal outcome. He could not believe that the vision of automatic computation was not transferable to his contemporaries by the successful completion of a machine. It was a saga which is a Victorian soap, a beautiful countess, a flaming row with the Prime Minister, public accusations of profligate and wasteful spending, experts who disagreed about the basic utility of the machines, and a walkout by Babbage's chief engineer, Joseph Clement. All this we relived in the modern construction, with the possible exception of the beautiful Countess. This is Babbage, demonstrating that's Babbage. That's the very first difference engine. And this is Babbage demonstrating his theory of miracles at one of his soirees to Ada Lovelace and John Herschel. The reason the picture is very blurred is because digital photography wasn't very well developed in the 19th century. I'm going to skip over the analytical engine. I lied to you about the sleeping accommodation, and to treat the analytical engine would require us to avail ourselves of it. So I will that is the 1840 plan of the analytical engine, 6 to 8 foot across, 15 foot high, entry-level machine. This has 20 registers. That's the plan of registers. Entry-level machine is 100 registers. Babbage spoke of machines with 1,000 registers. You're talking about an entry-level machine the size of a small locomotive, and you're talking about machines half the size of this room. So this was a quantum leap in logical complexity and physical size. There was anything like it that preceded it. I'll deal with the analytical engine in more detail on May 10th. I'll simply list the logical features the analytical engine embodies, and that is almost all the essential logical features of a modern digital computer. So again, for the tech wonks. Programmable, using punch cards. Internal architecture, von Neumann, Saw and Mill separation. Serial fetch-execute cycle, conditional branching, if-then statements. Iterative looping, microprogramming, pipelining, anticipating carriage, internal repertoire of automatic operations, 500 to 100 digit precision, parallel processing, output in printed form, stereotyped, punch cards, and graph plotter. And he considered other number bases, including binary, of course, 3, 5, 12, 16, and 100. That's just some of the features embodied in the design. So, the question, this is not a question of suggestive hints. This is not a backwards projection from our own age onto the blank canvas of the past. This is not the coded vagueness of Nostradamus. This is not a parvenu industry dignifying itself by claiming false ancestry. I've absolutely no idea what that means, but it sounds terrific. These logical features are explicitly embodied in the detail of his designs, and calling Babbage the first computer pioneer is not a casual tribute. I will just illustrate now through some icons of the extent to which, just in case you think that the claim of him being the first pioneer is a casual tribute, is not the case. This is the plan view of the printer that you see downstairs. That's an example of his mechanical notation, a symbolic, a hardware descriptive language we evolved especially to optimize the designs. This is an example of Babbage's notation. He separated control from data. There's the control, there's the data, those are the inputs. This is, again, his mechanical notation, a complete symbolic system of language that he evolved to describe his engine. That is the complete description of the output apparatus downstairs, and that's the apparatus. So that, if you like, is the mathematical description, the mechanical description, the symbolic description, and that is the apparatus. It consists of 4,000 parts. So, as I said, this isn't the coded vagueness of Nostradamus. This is actually, these features are explicitly embodied. That raft of logical system and circuit functions is actually explicitly embodied in designs. I should absolutely emphasize Babbage nowhere used those terms. He did not use words like pipelining. He did not even use the word programming. They are backwards projections from our own age. It's a terminology just to convey to you that there is an ancestry, there is a history of computing, and these logical functions were conceived. One might speculate whether it's an accident that the von Neumann architecture with the fetch-execute side is embodied in the very first conception of a computer before there was anything to give him any cues about it. To difference engine number 2, finally. That is the main elevation of the machine. It is one of 20 main drawings that he left, and it's one that is most evocative of its overall shape and use. And you can see the close resemblance to the one downstairs. It was designed between 1847 and 1849. It consists of 8,000 parts. It weighs between 4 and 5 tons. It's 11 foot long and 7 foot high. It's made of bronze, cast iron, and steel. It's a design of extraordinary elegance and economy. It benefited from his work on the Analytical Engine and incorporates a lot of the sophistication. The printing apparatus is quite interesting. It produces output not only in printed hard copy, but also produces stereotype plates for use in a printing press. It is programmable. You can change the format of the results on the page. It has variable line height, variable margin widths. You can print in 1, 2, 3, or 4 columns. You can leave gaps between lines, groups of lines for ease of reading. It will print line to line. It will print down the page and automatically fly back for a column wrap. It will print across the page and automatically line wrap. This is before Windows. There is an affinity with Windows. This machine crashes at least as often. And I'm utterly ashamed at how much enjoyment it gave me to say that.
Yeah, because it's done now.
Yeah, that was a cheap shot, I'm sorry. Okay, how complete design? Finally, last point. How complete are the designs? There were 20 drawings. They completely describe the engine, but there's insufficient information to give the drawings to the machine shop. The kind of information it lacks is there is no tolerancing because standardization didn't exist. There's no choice of materials, method of manufacture, and there's no indication of what kind of finish. All that had to be supplied from a knowledge of 19th century machine tool technology. We unashamedly used modern manufacturing techniques. We used numerically controlled machines and computer-aided manufacture. We had whimsical notions of doing this in period costume in the public gallery, one part at a time. But we would have had the same fate as Babbage. But the point is, we made no part more precisely than we know from measurement that Babbage himself could have accomplished. We took parts from Difference Engine 1 and we measured how repeatable could he make parts. So if you gave Joseph Clement, his chief engineer, a part and said, make me 100 of these, how precisely could he make the repeatability? To within what tolerance? 1.5 thousandths of an inch. We made no part repeatable to better than 1.5 thousandths of an inch. The precision is no more precise than we know that Babbage could have accomplished, but by other means. We did composition analysis on metals to ensure that we had the exact match. The whole point of this was an issue of authenticity. We had to resist the charge that we built the engine, but Babbage could not have. We would have indicated nothing if somebody could have leveled that charge and justified it. So the issues of authenticity were the watchword of the whole program. Did we have to do anything to make it work? Yes, we had to do tons. Okay, that's the back of the engine. Okay, I'm going to give you an example of some of the design. That's 20 minutes. I'm going to give you an example of some of the design, one of the design issues we have to say. Did we have to change anything? To what extent did we have to modify the engine to make it work? Well, I said authenticity was the watchword of the project. And I'll give you an example. You can see here, this is the inking mechanism. That's an inking cover, a lovely brass thing, which you can see downstairs. That's the ink bath. These are inking rollers and spreader rollers. Well, there's no visible means of support. Now, to build it... So what would it mean to build Babbage's design? You'd have to build the roller, you'd have to do that, you'd have to hold it here and then let it go. And we had a pretty fair idea that this wasn't going to work. So you can see that there were necessary interventions. But what we did was we did whatever modification we made. We firstly made it reversible. Secondly, we always used a solution that we'd found Babbage had used elsewhere in his designs. And that is the way we protected the issue of authenticity. The device we built is there. That's it. It doesn't fall down. Okay, how do you debug the machine? The machine jams. The machine is designed to jam. It's a digital decimal machine, which means that only integral whole numbers are legitimate. Any intermediate values tells you the machine is in an indeterminate position and the integrity of the result has been compromised. And the security mechanisms are absolutely effective in determining whether the machine remains digital. Problem is, it's a monolithic hardwired machine. Nobody ever designed or built something of this complexity. Had Babbage built it, you could be absolutely sure there'd be the equivalent of test points. You'd be able to couple one section from another. This is pinned, hardwire, absolutely monolithically integral. When it jams, it's a question of trial and error. And so this is the first logic probe. What you do is you feel around looking for play to see where the jam is. And that's how it's hunt and peck, trial and error, and that's how it's done. The story of the build up to 1991 is told in the Cogwheel Brain in the British edition and the Difference Engine, which is the American Penguin edition. I believe there are at least 3 copies in the store. So there's a story which is told up to 91. The story of the building the printer is not yet told, except in the Annals of History of Computing in a short article. So I'm going to end there with just the sumptuous thing and now introduce Nathan. I first met Nathan in March 1997 when he visited the Science Museum to see the engine. This was after a 1-year email courtship in which I wasn't entirely sure who I was communicating with. The arrangement was a very unusual one, that I was looking for sponsorship. The calculating section of the engine, which goes from there to there, up to that point, had been built for the bicentenary in 1991. I needed the rest to build the printer. The printer is an integral part of the engine. The machine is incomplete without it. So I was looking for sponsorship, and Nathan came to see the engine. And the arrangement was an interesting and unusual one. And that is that Nathan agreed through generosity and vision to sponsor the construction of the Science Museum's printer output apparatus. And also, part of the arrangement was that we will build him a duplicate for his own collection. And so that is actually how the machine came to be downstairs. This is Nathan's machine on loan to us, to the CHM for 1 year. And the second machine is, in a sense, part of a curious deal. I know you won't believe this, but it's true. There is no contract between us and Nathan, between the Science Museum and Nathan. This was a gentleman's agreement done in emails. I know Len does not believe this. This is America. What's that? We have lawyers. And they are lawyers, and they need to be fed. Yeah, I think you should start them too. So Nathan funded the construction, and it's through his vision and generosity and support that we've finished the first engine, and also that we have one downstairs. So, if you like, this is as far as I can lug this machine. This is, if you like, the handover to Nathan. The machine is now in the States. There are arrangements in place for Computer History Museum to transfer that machine from here to Nathan. So this is the fulfillment, if you like. It's 5 years late, but what's 5 years in 150 years? Of the presentation of the machine to Nathan, and this is the fulfillment of a gentleman's agreement between Sir Neil Cousins, then director of the Science Museum, and me, to Nathan. And all that there is in emails, and I've got the only file. And there were absolutely no problems. So, I have two stories to tell you about Nathan. The first is when we met, I showed him the engine, and I babbled about what I was trying to do. I asked him whether it was okay if I spoke about polynomials. I might even have asked him whether he knew what they were. I had absolutely no idea. He had 4 PhDs. He had studied advanced mathematics. And it's his reaction, actually, which is the point of the story. He was terribly gracious. He did not embarrass me, but he did give me an odd look. The second story is about delays. The engine was late. It was 2002, and I knew Nathan was building a house. And I said, when do you need your engine? When do you need your engine? At the other end of the phone, there was this burst of laughter, and I hope we will have the pleasure of Nathan's burst of laughter this evening. There was this wonderful burst of laughter, and he said, one might question, he said, the use of the word need. I'd assumed that gentlemen of Seattle, after supper, billiards and brandy, knocked off a few polynomials. He was limitlessly patient, always encouraging and ever understanding. I'm personally limitlessly indebted to Nathan for giving me the opportunity of finishing the first Babbage engine. And I think we all are grateful and indebted to him for allowing us the opportunity of having his machine here. Nathan.
That's one way to keep me from speaking, is to keep clapping. It's a great strategy. So I have to say, during the email courtship, no complaints about Windows crashing. So I've not told Doron this, but the first that I actually heard of this is there was correspondence that had come into my office, and my secretary came and they said, well, a Mr. Swade of the Science Museum in London would like you to read this. I looked up and I said, and what would Miss Velvet like? Because I'm thinking, yeah, right, there's somebody named Mr. Swade. But without Doron, none of this would have happened. One of the great, and sometimes, believe me, I've cursed him for that. One of the things I love, there's many things I love about this project. It's an example of experimental history. You know, there's a proposition. The proposition is that Babbage was too far ahead of his time. He wasted all this time trying to build something that was just not buildable in his century. Or with that technology, that a programmable computer is not something one should make out of bronze and steel, but he didn't know any better. And the amazing thing to me is that it was a testable proposition, and that someone rose to the challenge of testing it, and that someone was Doron. And we know now that had Babbage been a little bit more like Doron, the damn thing would have gotten built in 1850. Or maybe 1875, counting the delays. No part of this project has been easy. And I actually came to feel a great kinship with Babbage throughout all of this. Most communications from Doron, they were always incredibly polite and incredibly formal and wonderfully witty. But news from Doron, it was never good news. Okay? It just was never good news. I'm sorry. It's like, okay, what now? Up until the engine arrived just a couple weeks ago from London, we actually shipped it air freight. That you could ship something like this in an airplane was amazing to me. That you could charge that much for shipping, that was amazing to me. I thought maybe I should just send my plane and they can keep it. But it turned out they damaged it in shipping. And so the last 2 weeks, Doron and some people in the Science Museum and volunteers here worked feverishly trying to both polish up some defects and realign the whole machine. In October, we were supposed to have this event. You may not know this, but we were supposed to have it in October, but it turned out that a subcontractor building the last piece, the last finishing touch on this engine, ruined the whole stack of cams, and so we had to start over on those. And this but this has been almost 10 years of that. But through all of that, Doron persevered. So he really has a personality that the Babbage lacked. And fundamentally, the issue with Babbage, now that we've done the experiment, is we know he could have built it in that time. He didn't know how to manage a large, complicated project. Earlier today, I was interviewed by the press, and somebody said, well, what relevance does this have for today? I said, are you kidding me? Within 10 miles of this building, there's at least a dozen teams with brilliant people not getting traction because they can't manage a complicated project. Babbage really was one of us. Some of the other things that I love about this project and the machine, one is that the computer industry tends to be very myopic in some ways. Any one of us who've been in the industry knows that it's about performance and features and being on the cutting edge. And there's this huge tendency to talk about the version a year from now as if it's in the present tense, and to talk about the one 2 or 3 years from now like it's around the corner. We're obsessed with the future. We're obsessed with growth. And hey, it's been a great thing because we've actually delivered on lots of growth and a tremendous increase in capability. But one of the interesting side effects of this obsession with growth and the future is we forget the past. A machine that's old is junk. It's not something to be revered or something to be learned from. It's junk. So Silicon Valley and the technology industry tends to be a community that drives with no rear view mirror. Why would you look back? As a result, it's very rare to see people save or conserve or honor or display old computers. Downstairs in the museum in the visible storage exhibit, for example, there's an amazing set of the machines that made Silicon Valley. But it's probably one of the few places in Silicon Valley you can see that, one of the few places in the world, actually. One of the other places is a set of warehouses in the Seattle area that I have. Somebody asked me earlier, well, why don't you collect current computers? So I looked at them like, what makes you think I don't? But another thing that's a big difference that you can see immediately is that current computers, for the most part, are large beige boxes. Sometimes it's not beige, sometimes it's blue. But a large computer today is a rack mount in which people have stuck effectively lots of little PCs on cards. It's not very interesting looking. If you go back 20 or 30 years, you get to machines that were much more visually interesting, like the Cray. There's a Cray 1 downstairs. I've got one of those, and I've got a Cray 2, and a YMP, and an XMP. Those were cool machines, but actually mostly cool when you looked inside. If you look at the picture of a chip, you look at the floor plan of an Intel chip, for example, that's a thing of beauty. But that's all hidden from us in this, gray ceramic case. It's not very interesting. But in Babbage's day, his instrument, and actually many instruments of that era also, whether they were telescopes or microscopes, they were works of art. They're beautiful. Today, I got asked about 300 variations of the following question. Why did you do this silly thing? And sometimes they asked it very politely, sometimes they were about that direct. And if I was standing in the machine, I said, well, look at it. Look, if you don't get it after looking at it, I'm not going to be able to explain it. Now, Babbage is another interesting aspect of this is that Babbage really did anticipate our industry. There was a gulf of technology, and as I said, management and some other implementation issues. But he really anticipated an era where machines would think. The machines would do calculations for us. A completely nutso thing in his era. This was not a thing when people were asking when is Moore's law going to end, or how can I avoid the blue screen of death, or whatever it was. This was an era where the very notion that people would try to do the calculations behind this was a crazy notion. He believed in it. And when you read his books on the topic and his articles, you can see that he was a thoroughly modern speaker. thinker in how he thought about computing. Now, it took 150 years for his dream to come true. And over that period of time, there were all kinds of other false starts and eventually the correct starts that got things going. We'll never really know whether Babbage, had he succeeded, would have made a huge difference or not. There's a great book, science fiction book called The Difference Engine by William Gibson and Bruce Sterling from the 1990s that speculates about it. And it's probably at the far extreme edge of speculation, but they paint a picture of a Victorian world that was not just a world of steam power, which it surely was, and telegraphy and a whole variety of other photography, but also an era of computation, a Silicon Valley in the age of coal and steam. Could it have happened? I don't know, but I have been very proud and happy to be associated with this. I'm thrilled that Doron gave me the opportunity. It was, usually when people ask you to hug a tar baby, the right thing to do is not to hug it. And there were many times when I thought this was going to be a tar baby that I was going to regret hugging, but by God, he saw it through. It exists. We got it here. I'm thrilled to be able to share it with everyone here in Silicon Valley for a year. And then I'm going to take it and put it in my living room. And it won't be the strangest thing in the living room. So anyway, with that, I don't have any further remarks. I think we're going to go on now to some discussion. If I ask Len and Doron to come up here.
You like some water?
Oh, one other thing I have to say. There is only one person in this audience that is longer suffering and puts up with adversity better than Doron. And that's my mother, who's sitting here. When she had to deal with me, I would have tried to build it. It turns out it's much more manageable if you just pay for it. I learned that over time. Anyway, please continue.
Great, thank you, thank you. Fill out your cards, by the way, if you want to ask questions. Let me start with an easy one. Doron, you talked about the things you needed to add to the engine to make it work. Struts to increase the structural stability, things to hold up rollers that otherwise weren't held up. But you didn't say whether Babbage made any mistakes. It's hard to believe that in the design of a machine with 8,000 parts that he wouldn't have simply had bugs, did he?
Yes. There are various categories of mistakes. There are redundant assemblies. There are omitted assemblies. There are inconsistently dimensioned parts. You find a part dimensioned one dimension in one drawing and differently dimensioned in another. You have to resolve these. The trick was, the problem was, to resist the charge you built it, but Babbage could not have. And so the question is, how could we responsibly make alterations? The point about all these design errors, design mistakes, is that none of them compromised the basic logic. These were issues of engineering. They were not issues of engineering principle, they were issues of engineering practice. And the big breakthrough came when it was a realization that Babbage's design was not a work of unimpeachable perfection. This was an arrested engineering project, and we were just carrying it on. And that's how we broke that paralysis of saying we can't change anything. We knew if we built it the way Babbage drew it, it wouldn't work. How could we responsibly change it? But then would we have built Babbage's engine? And it was that breakthrough, saying this is not a work of unimpeachable perfection. This is an engineering project that had been arrested, and we were just picking up 130, 140 years later.
But you have the advantage of CAD design tools and simulations that Babbage didn't have. What did he use to design this engine?
We didn't use any modern technology, other than manufacturing technology, and I explained earlier that that didn't compromise the basic precision. We used conventional pen and paper drawing. We produced 150 drawings from the original 20 which specify each of the 8,000 parts with sufficient manufacturing detail so they can be made in a modern machine shop. And we used numerically controlled machines and computer-aided machines. But we used no design aids. We used no electronic design aid. This was conventional draftsmanship on a drawing board with a very experienced, wonderful engineer called Reg Crick. So Babbage made no mistakes that affected the fundamental logical principle of his machines. There were a lot of practical things we changed. There was only one device which we had to redesign, and that was the clutch, which rewinds the weights in the printer. And that was because he was trying to turn something and slide it at the same time, and the torque, the turning force was too great to allow the thing to slide. So we just redesigned the clutch in the same space, using the same principle, but just slightly elegant. That's the only thing we needed to change.
Did he make test pieces for the Difference Engine No.2 to see if things would work at all, or was none of it built?
None of it was built. By this stage, he had so far advanced beyond Difference Engine 1, he had already designed the Analytical Engine. This was a kind of masterwork of economic elegance. He visualized it all. He did not need to build any of it.
Nathan, let's speculate about why Babbage failed. You talked about essentially project management, but was it also a lack of infrastructure? If Babbage had had a Silicon Valley-like environment when he was alive, would that have helped?
Well, undoubtedly it would have. You know, there's the printer less so, but the core part of the calculating engine has got lots of identical parts. And an industry to create lots of identical parts was not something that was routinely done. So there certainly would have been an issue with that. The tolerances were within what people did, but the total number of parts was not. So I think that if there had been people building 2,000 and 3,000 part devices routinely, then absolutely building the 8,000 part device would have worked. And if he'd gotten there, going to the Analytical Engine that had 100 different core units and so forth, you could have imagined scaling up like that. And in fact, the Victorians did scale up when it came to building ships and bridges and locomotives and steam engines. So there's a variety of areas where the incremental improvement thing, which is what the way if we built one of today's computers from scratch, it'd be really hard. But of course, we're making a set of things inheriting all of what we knew from the past. So undoubtedly, it would have been easier for him. The trick is his role, he didn't know it, but his role was to get the snowball rolling down the hill at the start. He had to bootstrap the creation of that infrastructure, not rely on it. And that's always harder.
Right. I don't know if you know, we have a volunteer who builds Babbage-like engines out of mechano parts, out of erector sets, basically, leading to the speculation that if Babbage had had an erector set, he wouldn't have been a failure.
Oh, I pointed this out to Tim earlier today and said, you know, what would Babbage think of this? Because Tim has built with these mechano sets, he's built far more than Babbage ever managed to get built. But that also speaks to this notion of infrastructure, the notion of modular parts that you can easily reuse. And in this case, everything that Tim used to build those things was standard parts except for the long rods. Right. So that you could do that is astounding. But it speaks to the fact that the whole concept of erector sets, or as they call them in written mechano sets, that whole concept of interchangeable parts and modularization was a concept that didn't exist. Try to build anything complicated without there being standards, and you find it's way more difficult.
Tim is prototyping some of the Analytical Engine, which leads to the question of whether you and Doron are having an email correspondence about the next project.
Lunch today, actually. You know, it would be wonderful to see the truly programmable machine built. It's a task even more difficult, I think, than Difference Engine No.2. A lot more extrapolation would have to be done. And of course, part of me is thinking, well, maybe I shouldn't be having lunch with Doron. Maybe it should be with Tim.
It'll probably be a lot cheaper.
We need to make a slight correction here, and that is Nathan has already funded some of the Analytical Engine. The printing apparatus for Difference Engine 2 is a common design. It's shared between the Analytical Engine and the Difference Engine. So strictly speaking, we in fact already have a piece of the Analytical Engine.
Have a piece of it. Yeah, it's the rest that we're talking about.
That's trivial.
The analytical engine, of course, was a real computer. It was
Yeah.
a computer, which he failed to build. And I sometimes say that that began 100 years of dark ages when people never again tried to do that. Did he really have that effect? It seems to me a computer could have been built in 1910 with relays if somebody wanted to.
Oh, sure.
Did Babbage
Conrad
influence
Zuse
the
did
fact-
with relays not that long after that. I mean, not in 1910, but in the 1930s and 40s, he built some relay machines before switching to tubes. They certainly could have.
I guess what I'm fishing for is, did Babbage really have a negative effect, or was it just that there wasn't any other need or driver for that?
Maurice Wilkes, man who built EDSAC, pioneer of electronic computing in England, the EDSAC was based on the ENIAC, accuses Babbage of having delayed the development of computing because he became associated with failure. And we have a specific instance which I found, which is that the Fowler calculator, Thomas Fowler developed a calculator, a three-state logic calculator, that in a sense was vastly more promising than Babbage, exactly contemporary with Babbage, that was refused funding because of the bad experience the government had had with Babbage. So Wilkes did not know this when he made that speculation. And I since discovered there is an historical instance which actually supports it.
Interesting. Talk about the reliability of the engine. How does the reliability of Babbage's engine compare, for example, to the first computers that were built in the 1940s?
I've had my cheap crack about Windows.
That's why I said 1940s.
No, it'll be a very expensive mistake.
Well, there you go. Reliability. The machine is very reliable once it is adjusted and run in. The machine in South Kensington in London is operated routinely. It is very rarely ever reset. We run the registers fully. It does take time to flush out the bugs. There are out-of-spec parts. You get marginal situations which coincide to produce jams and breakages. That will be the same with this machine. It's already started, but they drop out. The frequency of those drops, eventually the machine becomes more and more reliable, becomes easier and easier to turn. The one in London you can turn with one hand, and that's been running since 91, the calculating section. So when the machine is adjusted and run in, it is reliable. It's as Babbage said.
So the answer is we should keep running it.
Absolutely. Yes.
Hear that, Nathan?
Run it to destruction.
Well, maybe not. Of course, the early relay machines, relay machines, but the vacuum tube machines were very unreliable because the mean time between failure for vacuum tubes was at that time gated by manufacturing for radios, where you had very few of them. And so, mean time between failure if you have 10,000 tubes was really pretty poor. So the very first computers, ENIAC, for example, was not terribly reliable. The JOHNNIAC, the IAS computer, all of those, if you look back at the historical record, I have pieces of all of them. And so I've looked into the history, and they were all quite unreliable in some ways. One thing I should have mentioned earlier, another problem Babbage had, which is another classic Silicon Valley problem, is that he was a purist, and he massively overbuilt his design. So the difference engine calculates a seventh-order polynomial. Now, today, if you want to interpolate almost anything, whether it's a CAD shape in a thing, or it's fonts in a PostScript printer, or it's mathematical tables, you use cubic splines of some sort, Bézier's, a whole variety of cubic. Why do you need seventh-order polynomials, for God's sake? Some reason he built seventh-order polynomials. He built 31 decimal digits, that's 44.7 bits. Thing. Why did he need a 44-bit computer in 1850 when most of us in this room probably are still using 32-bit computers? I, however, switched over. Why did he overbuild it so much there? If you had been pragmatically minded, I think you would have said, look, let's make one that's, third order or maybe fifth order. Yeah, we got to reset it more often, but it'll be smaller. Let's put fewer significant digits in, and let's actually get the things in use. So let's get a few lead customers, and that is the way we all think today. That is how this industry was built: is finding some foolish early adopter who you When it comes to difference engines, I am the foolish, extremely late adopter. It's really silly to be the first customer, but the last customer is also pretty bad. That's me here. So besides project management, if you had gone and cut the order of the polynomials down, and you'd cut the precision down, and you'd made a smaller version, you probably could have made it a whole lot easier. But again, that's a classic thing. Lots of startup companies tank if people are too purist about things and hold out for the perfect instead of going for the good enough.
You knew 640K wasn't enough.
I was astounded the Analytical Engine might have had 1,000 registers. That was quite remarkable. Doron, talk a little bit about the venture capital funding back in that era. He got money from the government, but then the government's CTO, in a sense, the Astronomer Royal, panned the machine.
1822, 1823, Babbage had a meeting with the Chancellor of the Exchequer, and it was a very unfortunate meeting because it wasn't minuted. And Babbage, without question, left that meeting under the clear impression the government had undertaken to fund the machine. This was open-ended, no delivery date, no budget. The government gave him a blank check to finish the machine. That was his impression. He was doing this for the government, for the public good. He got £1,500 from the Civil Contingencies Fund and set off doing it. And the government honoured its obligation. Every bill he sent them, they paid. He paid out first and then recovered the money from government. And the government had paid out, by the time Joseph Clement's final bill was paid in 1832, the government had spent £17,500. Now, there are various ways of calculating what a modern equivalent is, but I reckon it's about $200 million now. And they had nothing. They had 1/7 of the machine 11 years later and 12,000 unassembled parts. One could say that this wasn't a great betrayal of government to pull the plug on the machine in 1842. Because what Babbage told him in 1842, he said, don't finish Difference Engine 1, even though you've spent £7,500 and 20 years on it. He said, build my Analytical Engine, or possibly even this Difference Engine, another Difference Engine. Scrap what you've already spent. He had no idea that it was much more important for him to finish an obsolete machine, to act as a stepping stone of credibility to the next one. Because he was a principled man, and he felt he was obliged to tell government that the machine had been superseded. As a matter of honor, he could not build a machine that had been superseded. So he was his own worst enemy. He had absolutely no political.
He would not have made it on Sand Hill Road.
So he was hugely well supported. He was a man of independent means, inherited the equivalent of about £100 million on the death of his father. He was a wealthy banker. That may be figurative, but he was an independently wealthy man. He could well afford to fund his own interests. Massively supported by government, who ultimately, out of perplexity and frustration, just pulled the plug in 1842 and said, you're welcome to keep all this, you've fulfilled whatever obligation we expect. Why he possibly started designing this machine in 1847, after he'd done it, was in fulfillment of the obligation, saying, here's a machine 3 times more efficient, 1/3 of the parts. You could build. He offered it to government. He didn't protest when they refused. He just accepted it. And the reason the drawings are intact is they never went anywhere near a workshop. Difference Engine 1, they're missing drawings, some of them all. This one, absolutely intact, and so we were actually in a position, mothballed, 130, 140 years later.
Some questions from the audience. This one may have something to do with your current job, Nathan. It says, did the 19th century patent system protect the inventor of machines like the Babbage engine?
I don't know if Babbage filed any patents on his machine. There certainly were a number of other calculating devices that were created in the 19th century, and typewriters. I have a big collection of typewriters, and typewriters contemporaneous with all of this, being developed in the 1830s, was a big spurt all the way up through the end of the 19th century. Was an incredible period in typewriters, and all kinds of patents for various aspects of it. So, yes, there was a patent system. The patent system in the United States actually started right with the Constitution. Thomas Jefferson and George Washington both signed the first U.S. patent. So it was around. I don't know the extent that Babbage would have done anything, though, because I think he viewed it as a government thing.
Scheutz had a patent on his engine.
Yeah.
Babbage was opposed in principle to patents. He said the discoveries of science should be for public benefit. So in principle, he would never patent anything. And it was
Like I said, he was messed up.
So even if, he wouldn't patent anything, he was, Wollaston, one of his friends, I said his friends could do no wrong, his friends could do no wrong, his enemies could do no right. He had a friend who knew, who had perfected the process of annealing aluminium. And he kept the secret. He made £30,000, which is an absolute fortune because he was the only one who could do it. Now this was in violation of Babbage's principle that patents should be, discovery should be public benefit. But the way, because Babbage's friends could do no wrong, the way Babbage redeemed him is that, I think it was Wollaston, just before his death he revealed the secret. And this redeemed him for Babbage.
Babbage.
Did the patent system in the 19th century protect the inventor or the employer?
Oh, actually, in the 19th century, virtually all patents were by individuals. Okay, so all patents were, the idea of a company that would pay someone to do R&D basically did not exist. So although companies bought patents, patents were virtually all individual things. It was individual inventors would do it. In fact, the interesting thing is that in U.S. Census, patent was a legitimate job classification until 1910. In the 1910 patent, they decided to eliminate inventor as a job category and put it under office worker or something like that. So in that era, everyone who had a patent to first order approximation was an individual. And yes, they could be very important. And there were a number of important patents and important patented inventions in that era, particularly around steam engines and valves for steam engines and so forth.
One of Babbage's problems was getting along with people, although you said his friends could do no wrong, but presumably his chief engineer was his friend, Clemens was his name, and he got into a spat with him. What was that about?
Babbage would not have had a friend who was a journeyman. Babbage was a gentleman. So there's an absolute class distinction. He would not regard Clement as his friend, he would regard Clement as his servant. So the spat with Clement was overcompensation. Babbage had a set of fireproof buildings, workshops, built near his house. And in 1832, after the trial piece, this demonstration piece of Babbage's had been built and delivered to his house in December 1831, Babbage wanted Clement to move his practice from Lambeth, which is 4 miles away from Babbage, south of the river, to his workshops. And Clement wanted £600 compensation. He said he would lose work if he moved his workshop, and that Babbage would become the sole client, and he would lose clients. And that is what the beginning of the dispute was, and it spiraled out of control. Babbage was a principled. He didn't think Clement had a right to object. And, he was touchy, principled, proud, found something to argue about, and the thing just spiraled out of control. There was nobody to mediate, and that dispute was never resolved. And
Why couldn't he hire someone else?
A very good question. Clement had owned the tools.
Were the tools unique to this machine?
Yes.
Ah.
And Clement owned the drawing. It took some while for Babbage actually to get them back.
Clemens owned the drawing?
By law in the 19th century, not the drawings, Clement owned the jigs and the tools that we used to make this machine. Right. And it took a while of negotiation, quite bitter negotiation, with the government and Clement and a fourth party involved, for Babbage to recover. It was actually during the period that Babbage was forced away from the details of the nuts and bolts of the machine, without his drawings and without the machines, that he conceived of the analytical engine. Because there he had the freedom to actually re-examine and revisit some of his earliest ideas. And the analytical engine actually grew out of the enforced gap between the Clement walking out, the project being abandoned, and Babbage taking off again. So why didn't he employ something else? He was quite discouraged. He then, by that stage, invented the analytical engine, which totally seized him. And he actually wasn't interested in the difference engine anymore because he wanted to pursue this grand dream of fully fledged automatic general-purpose digital computation.
Did he ever try to get funding for the analytical engine?
No. No. He tried to get funding for the difference engine too, but not that.
Nathan, question here. What is the strangest thing in your living room?
Me. But in addition, there's a lot of other weird shit there. I have a Tyrannosaurus Rex in the living room. The whole thing, full size.
That's pretty strange. Doron, in the process of building the difference engine, did you build any simulators, either before or after?
No. There was various student projects, one of them at Imperial College, that produced simulations of the basic logical addition mechanism, but none of this was used for its production or its design. We used traditional pen and paper drawings and modern manufacturing techniques.
What was the most surprising thing in building this engine?
That someone would pay for it.
The most surprising thing, I thought you were going to ask what the most difficult thing, and that's easy, people. The most surprising thing was the sophistication of a device, the purpose of which we couldn't actually fathom from the drawings. We didn't fully understand what this thing was, and we slavishly stuck to the exactness of the designs and built it, and when we saw it work, we were completely dumbfounded, because it's a device of enormous sophistication. I don't know if there's a few seconds to go into it. Sure. You've got a figure wheel. Values are stored on figure wheels with decimal numbers on them. So the more it turns, that's its value. The amount it turns is its value. Now, you'd think that, and a wheel meshes with it to turn it, and that's how it adds. Now, you'd think that because whether a wheel or not turns depends on the calculation, you can't know whether a wheel is going to turn in advance. So the wheel should be free to turn at some point in the cycle. Therefore, you should be able to walk up to the machine and derange it at the point at which it should, and you can't. Now, there are at least three methods that Babbage uses to stop this, but the one we didn't understand fully is that the wheel can only accept information from legitimate sources, from a wheel below, from a carry, and from a wheel on the side. And what this device did was, it dropped the mechanism onto this wheel at a point in the cycle where it needed to carry. And it stopped, if it didn't carry, it stopped it from moving. And that piece of sophistication was something we just did not fully understand. Perhaps we could have if we pondered it more, but we didn't. We said, we don't fully understand what this thing does. And when we built it and saw this thing drop, and we realized, and Babbage challenges you, he said, walk up to this machine and attempt to derange it deliberately, even while it's trying to calculate, and you will not be able to do so. And this is part of the mechanism that does that.
Why was he so concerned about deliberate derangement? Presumably, if the machine were unmolested and being operated, that wouldn't be necessary.
Well, if it's immune from deliberate derangement, presumably it's immune from inadvertent derangement. What he was worried about is drifting from a vibration. And the best example we have of a machine that was built which didn't have these security mechanisms is the Schweitz difference engine, which was known to be troublesome. They had to run it at the dead of night in quiet to hear its music, as far said. And that was smaller. It was a much more compact machine, more like clockwork than Babbage's engineering, and it did not have the security devices, and it was subject to derangement. So it was to guarantee the absolute integrity of results.
There's a question here that makes me realize we didn't answer a very fundamental question. It says, why is it called a difference engine?
It's called a difference engine because of the mathematical principle on which it's based, which is a method of finite differences. And the beauty of the method is that it allows you to calculate any polynomial which would ordinarily require multiplication, division, subtraction, and addition. And it allows you to do that calculation by repeated addition only. And that's a technique that was well known in Babbage's time, and it was used by the manual computers to tabulate, for subtabulation. So it's called the difference engine because it's based on the principle of the method of differences, and the beauty of the method is it allowed Babbage to just add with gear wheels and do effective multiplication and division, which was something hugely difficult to do, something he did much, much later with huge difficulty with his analytical engine. It allowed him to evaluate polynomials using repeated addition without having to design an automatic divide and multiply.
It's actually a descendant, in a sense, of a lot of methods, finite element methods, for example, that are used in calculating strength of materials, engineering calculations, even fluid flow, where you discretize things and break it down to a very simple finite difference equation. In this case, he was only trying to do polynomials, so they were particularly simple. But in fact, that same method is behind the structural calculations that were used to build this building, for example, almost certainly.
Right. Nathan, one of the reasons why we collect objects and stories about them is to be inspired by engineers and brilliant people of the past. Should we be inspired or discouraged by Babbage? He was obviously brilliant. On the other hand, he failed. What's the lesson that we learn from him?
Well, you know, the process of Silicon Valley and the technology industry is about trying to figure out what the next big thing is. And I think it's just as instructive to learn about the almosts as it is the ones that were great successes. So, of course, we should celebrate the notion that this guy came up with many of the fundamental ideas of computing. You know, the core belief in automatic machines calculating faster and with fewer errors than humans ever could. That vision is what built the whole information technology industry. We have to celebrate that. We also have to say it's a shame that someone that smart wasn't able to pull it off. Because we'll never know. It's possible that had he pulled it off, he would have had a slightly better calculator that would have led to a few other slightly better calculators, and it wouldn't have been this Victorian computing revolution that the sci-fi book describes. Or maybe it would. You know, we'll never know where it is, but I think that even though he didn't ultimately manage to succeed in his lifetime, he actually did succeed in ours. And that is something that we need to understand and celebrate in its own way.
Doron, this question inspires a question about the scale of the machine. It could have been built larger. It could have been built smaller, like a piece of clockwork. Why was it the scale it is?
That's a good question. It's a question we've speculated about. There's no clear answer. There's no clear answer from looking at the drawings. The answer that he suggested, having built the machine, is that one has to look at the relationship between the smallest part and the biggest part. To go any smaller would make the smallest part too fragile. And the smallest part is like clockwork. It's the one that keeps breaking. And if you made it any smaller, the forces involved in lifting all that steel, in the lifting and turning motions, would stress the smallest part. And if it was stressed inappropriately, it would strip. So that is probably as small as it can go without going into clockwork. And if it was clockwork, the thing would strip. Over here, you can get enough feedback at a breakage to stop. You still get the breakage, but you don't strip it.
Was Babbage doing this analysis quantitatively? Was he doing calculations, or was it intuitive?
I think it was intuitive, but there are instances in which he has controlled breakages. Not on the machines, but in his railway designs. He had a system where he would actually make an incision in a member so that if it broke, it would break in a controlled place. Yeah. And so there is
mechanical fuse.
A mechanical fuse, wonderful, yes. So there are instances in which he thought of that. The other reason it is big is to make space for his security mechanisms. Each wheel has 4 decades. It doesn't just have 10 teeth, it has 40 teeth. And it's to get a big enough scale to have the locks come in so that he can afford the security. Security mechanisms are absolutely imperative. He has to have it as a digital machine that guarantees integrity. Otherwise, there's no point to it. It's not a question of this may be right. He has to know it is right.
You know, I have lots of old calculators. You know, within the decades after Babbage, people built various commercial calculators, much less sophisticated things generally that would add and subtract is the primary thing. Then you started getting in ones that could multiply. All of those calculating devices were far, far simpler and were smaller. They're bigger than calculators today, obviously. The arithmometers, for example, are about this big, and they're brass and they're beautiful. And they actually were quite practical, but they were set up for doing smaller scale things. For someone, much like you'd use a calculator today, not doing an industrial scale calculation of a giant set of tables or with sophisticated polynomials as Babbage did.
You keep talking about your collection. I don't know whether I should be pleased or worried. Are you going to be starting a museum? Are you competition? Doron, why don't you talk about some of the other things Babbage invented? He wasn't only a designer of calculation engines. He did other things as well, didn't he?
He invented the first ophthalmoscope 4 years before Helmholtz, to whom it's credited. What is not well known at all is that Babbage had an eye defect. And for someone who was something of a drama queen, it's quite, I'm talking about Babbage, not me. For someone who was quite, I wouldn't say self-indulgent, but he made a fuss about things on principle. It's extraordinary that he only wrote to one person about it. He didn't actually ever mention it. And what he did was, what's regarded as a manifestation of eccentricity was that when he did his tables, he actually printed the results on every different kind of ink, on every different kind of paper, including green ink on green paper, to see for the ergonomics of reading it. And everyone thought this was slightly daft. When you look at the fact that he may have had an eye defect, and if you read the preface to his books, he talks about ease of reading for people with difficult sight. So he invented the ophthalmoscope as a self-investigative device to find out what his eye defect was. And he took it to Wharton Jones, who was the most celebrated, what we now call an ophthalmologist. He was an optical surgeon in those days. And Wharton looked at it, saw a red blob and said, this is worthless. And admitted later, 4 years later, when Helmholtz came, that Babbage had actually invented that. The range of things he invented is rather astonishing. He invented a seismograph. He invented a device for ships traveling upstream against the tide. He invented, the first noughts and crosses, tic-tac-toe device.
A device to automatically play tic-tac-toe?
Yes, as an arcade game. Oh. And you would challenge the device.
Why didn't we build that? Wait a minute!
Probably would have been much cheaper.
Now he tells me!
And the money he was going to make from the arcade game, he was going to fund the Analytical Engine.
So seriously?
Yes, he writes about it. So the range of his interests was massive: lockpicking, chess, submarine navigation, compressed air-propelled submarines, diving bells, funicular mail delivery systems. That you'd have strings with bags which ran pulleys across church steeples that would deliver mail between...
Mechanical email.
Mechanical email. And he started this between his living room and his workshop, and he developed this into a national automatic mail delivery, funicular mail delivery system. He invented shoes for walking on water. He invented...
Is that because he couldn't swim?
He nearly drowned at 16. Yeah. But I should say he nearly drowned testing his shoes for walking on water. He invented a cowcatcher. This was the boom of railways, 1830s, and he was dining with, I think, American railway investors, and they were complaining about delays caused by cows on the line. So on the back of a napkin, he sketched 2 cowcatchers. So it just goes on and on. I mean, this was a prolific inventor. And the range is just extraordinary. Locks, chess, all this stuff. Yeah.
Did he ever have any collaborators, or was all this done completely on his own?
He was pretty well worked on his own. Very few people knew about the Analytical Engine. He never lectured in the Analytical Engine in England. He gave one lecture in Italy in 1840-41. McCulloch from Scotland was present. He was, as far as you're aware, the only Englishman who's ever heard Babbage talk about his Analytical Engine in the form of a seminar. So he worked essentially alone. Yes, he worked essentially alone.
And it was that one lecture, if I'm correct, that led to the path for Ada Lovelace to learn about the machine? And was she the world's first programmer? We hear people saying that.
Nope. Okay, you want the 30-second Lovelace story?
Sure.
Okay, Lovelace is celebrated for 4 things. She's the prophet of the computer age, she's the first computer programmer, she was a brilliant mathematician, and she collaborated with Babbage and was instrumental in the conception of the Analytical Engine. 3 of those propositions are absolutely false.
Lord Byron's daughter counts for something.
She was Byron's daughter, which is true. Now, she was not a brilliant mathematician, she was a mathematical novice. She may have been very clever, but Babbage was a mathematician, and he's not a great mathematician, but he'd published 13 papers by the age of 21. He left no mathematical legacy, he discovered no new theorems, but he was a mathematician. He was a crack mathematician at Cambridge. Lovelace was a novice. She had Augustus de Morgan to tutor and so on. So she may have been a brilliant mathematician, but nobody knows because she's... right, she was not a brilliant mathematician. She collaborated with Babbage, was instrumental in the conception of the Analytical Engine. Ada Lovelace was studying the method of differences after Babbage had conceived of the Analytical Engine. Ada Lovelace was studying methods of differences, which is his first one in 1821, after 1834. So she didn't, she was hugely instrumental. I will tell you what Ada Lovelace should be famous for, and she absolutely deserves the ways in which she's celebrated now, but for none of the reasons that I've so far mentioned, or one of the reasons that So, a mathematical genius, first programmer. She is known as the first programmer, and that is an understandable and excusable misconception. And the reason is she was the first person to publish what we would now call a program, that is an algorithm, a stepwise process for finding a solution. And she was the first person to publish it. If you go to any published source, Ada Lovelace is the first published. But the examples were Babbage's used at the Turin lecture in 1841. So Babbage was the first programmer, Lovelace was the first one. So we've got collaboration with the Analytical Engine, mathematical genius, first programmer. But she was a prophet of the computer age. She saw something Babbage did not see. The fundamental transition from calculation to computation is Lovelace's. And the fundamental difference is to go from a number representing something other than quantity. A computer is a machine that manipulates symbols according to rules. A calculator is something that manipulates numbers for the purpose of manipulating quantity. And it was Lovelace who saw this, and she wrote explicitly about this in ways that Babbage did not. And this is the integration, if you like, of the poetic mind and the analytical mind, if one likes to speculate in that way. This was a cast of mind that allowed her to see what Babbage saw the machines always bound by mathematics. He saw the machine as an algebra machine. That's a general purpose thing where you can manipulate a symbol regardless of its numeric value. But he did not see the notion of a quantity representing something other than number. A quantity representing a letter of an alphabet or a note of music. And this is Lovelace not just making the suggestion, she is banging on the table and saying, this is what is important about the analytical engine.
But Babbage was a brilliant man. You think that he would pick up that thread and elaborate on it. Did he know what she was saying about the usefulness of his engine?
He said that now that he'd read the notes, Lovelace's notes, he realized he perhaps should have speculated further in this way. But that's as far as it went. Babbage never saw the device beyond number, and Lovelace did. And she was the one who wrote in this very poetic way about the analytical engine weaving patterns in numbers, the way the Jacquard Louvre weaved patterns of leaves and flowers. So she was the one who had the vision to see this, and this is absolutely explicit in her writings. And Babbage did not pick it up and didn't speculate on that any further. Yeah. So she was a prophet of the computer age. She saw the significance of computation as a model. Babbage saw the significance of computation as a systematic method of solution, always bound in mathematics. Lovelace saw you could get quantity to represent something other than a number to represent something other than quantity. And that is completely anticipating Turing. The Colossus was the first machine to actually manipulate quantities which represented letters of the German alphabet. So, should she be celebrated in the way she is? Absolutely. But for that reason, that fundamental, if you sift back in history for that essential transition from calculation to computation, it's Lovelace who did it.
Okay. I think that's it. Thank you both very much.
Terrific.
These are photographs from Mark Richards, who produced the Core book that is on sale down in the bookstore. They're exquisite photographs, limited editions.
Oh boy, just what I need.
You're not going to get your engine for another year, so you can put this up in the wall right where the engine's going to go. Thank you both very much.
Thank you.
Delightful evening.